Yeah, welcome once again to my YouTube channel on data analysis and research. Today I want to look at the Bland-Altman analysis. I've previously done a video on this, but I used a different statistical software. Today I want to use another one, a statistical software called the MedCalc. So that one is quite simple, and you don't need formatting to create the Bland-Altman plot, unlike using the graph path present. So this one is much simpler, and I want to demonstrate how it is done using MedCalc. So first we'll open our software. So this is MedCalc, statistical software. Okay, so this is how MedCalc, the interface look like. So you see the tools here. So you have file, edit, view, format, and all that. So we don't have data in it, so that is why it's looking very blank. So we have to import our data. So the Bland-Altman is normally done to test for agreement between two methods. So you have a standard method, a gold standard, and you have another method which has been developed, a new method that might be simpler or cheaper to do what you want to measure, but you don't know how reliable it is as compared to the gold standard. So you normally use the Bland-Altman to gauge the level of agreement or measure the bias, the differences between the two methods. If they agree, then it means that one method can replace the other. So that is how it is done. So I'll import the data. So so this is what I'm looking for. It's in Excel. So we select it. Then if your Excel has different pages or sheets, you need to select the sheet that your data is. So I will select mail. That is where I have my data on. Okay, click OK. So here you can see there are two columns of data. So OH is observed height. So we are using height as an example. So observed height means that this is the height that you have measured, or height that is actually measured using a stadiometer or a wall meter. So that is the actual height measured. And now this is predicted height. So predicted height is using another method to estimate the height without measuring it directly. So in anthropometrics or anthropology, or even in statistics, there are equations called models. So you can create a prediction equation based on another human uh, part, say the female length or the ulnar length. You can use the ulnar length to predict the height of a person. This is normally used during investigations where there are suspected cases of murder or suspicious death, said that you do not find the entire skeleton of the person. So you can use a body part to try to estimate the height of the missing individual. So in this case, the height has been predicted. So, but how reliable? How does the predicted height agree with the observed or the actual height? So that is where you use a Bland-Altman to measure how the two agree. So in MedCalc, to do the Bland-Altman, perform the Bland-Altman analysis, you go to statistics here, and then you go to see method comparison and evaluation. So you want to test how reliable the second method is compared to the gold standard. So here the gold standard for height is to measure it directly. You measure it directly, so you know that's the height. But in the case that you do not find a full skeleton or a full human body, can you use the ulnar length to predict the height, and how reliable is that? So we use Bland-Altman plot. So select this. So the first method is what? So it's comparing two methods. We want to put the observed height there. The second method is the predicted height. So there are various ways that Bland-Altman can be plotted. So mean of both methods. You can use the mean of both methods to do, but you also have the mean of the first method, mean of the second, geometric mean. So if you have data that is mostly non-parametric, you might go this way. Sample rank, also for non-parametric. So rank for first. So these are for non-parametric. Usually this for parametric methods. So usually the common one is using the mean of both methods. You can also plot the differences or plot the difference as percentage. So here you just plot the differences, or the second method you can plot it as a percentage, and then the third one as a ratio. So let's stick with the first one, just the differences is okay. So here to draw a line of equality to using the difference. So 95 confidence interval. So you can plot the 95% CI of the limits or not if you wish. So you can plot for the limits or not, or for the difference. So whichever you choose to do, that is fine. So I just want to make it simple, so I will not select any of them. Okay. So this is just what you do. Then go to OK. So our plot is here. Let me enlarge it so that you can see well. So you see the Bland-Altman plot. So this is the mean of the observed height and the predicted height. It's plotted on the x-axis, and the difference between the observed height and the predicted height is plotted on the y-axis. The line in the middle, the blue line, is a measure of the bias. So ideally, if two methods agree perfectly, then this blue line should be on 0. The bias should be 0. There should be no difference between the observed, or the gold standard, and the alternate method. But here you see that the blue line is not on 0. So the difference between the means of the two methods is 2.8. This is called the bias. So this is the bias, the deviation of one method from the other. So the bias tells you something. This bias is obtained from the actual height, that's the gold standard, minus the second method. So if it's positive, what does it mean? So it means that the actual height is higher than the observed height. So that is why you have a positive value. So meaning that the second method underestimates the height by 2.8. If this was negative, it means that the second height overestimates the height by 2.8. So the sign is important. So in this case, the second method underestimates. Okay, but we want to see, that is not all. Is this difference significant? So sometimes you can have a bias, but statistically it is not significant. So meaning that you can still use the two methods alternatively. You can use either one or the other depending on the simplicity and the cost. So having seen the bias, this is the agreement, the limits of agreement. So how wide is the agreement? So for a good method, this limit should be narrow. So if you have a second method where the upper limit is at 5 and the lower limit is also at 5, it will be a better method than this one. So the limit should be very narrow. Limit should be narrow. Bias should be as close as possible to 0 to give you a good method. So you can see that the limits of agreement is so this bias, the 95% confidence interval, so it lies within minus 6.5 to 12. So this is the mean plus the standard deviation. So that's how the limits are calculated. Okay, so you can see the individual data points scattered all over. So this is the distribution. And you can see that most of them, at least over 90 or 95%, should be within the limits. So that gives you a good method. So any data point lying outside normally indicates that there are possible outliers. So, but majority of the scatter dots should lie within the limits. So, having looked at the plot, so let's see whether uh, this agreement is wanted to see the some produce p-values to indicate whether it is significant or it's not significant. Okay, but in general, so that is just how this is done. Bland-Altman in MedCalc. So if you have previous studies that have also done this, you can compare the bias 2.8 to it and see which one is better. Or if you have done several comparisons. So if you have two methods and the bias is the same 2.8, then you have to come and compare the limits. So the one with the narrower limits of agreement will be a better method than the other. So this is how you do Bland-Altman plotting MedCalc. But before you go, please subscribe to my channel by clicking on the subscription button below. Also like and also share this channel to your colleagues who are interested in data analysis and research. So see you next time for more free tutorials in data analysis and research.